So, four identical particles of equal mass are moving along the circumference of a circle under the action of their own gravitational attraction, and we are required to find the speed of each particle. Now, this is a question of gravitation, and we need to notice few things. First is that the particles are all identical. So, what this does is it simplifies the problem in terms of configuration. Whenever we need to solve such questions, we must first think about the configuration. So, the step one should be to think about how the figure will look, what will be the visuals of the problem. Now, let's imagine a circle and there are four particles and they are all identical. So, what this does is that these particles cannot be asymmetrically placed around the circle. So, let's imagine I place them randomly on circle. Now, why this cannot be the configuration is because then just think from the perspective of one of the masses. This mass can say why this other mass is at a distance of d from me, but this mass is at some other distance d prime. Since we are all of the same mass, so there should not be any misconfiguration with respect to my position in the configuration. So when you place these masses randomly, this creates imperfection in the configuration. So the only symmetrical configuration that this system can take is when they are all identically placed. So there is no difference. They are not differentiable from each other's perspective. And the configuration that this makes is they are equidistant from along the circumference. So this is the resulting configuration. These two masses are diametrically opposite and these two masses are diametrically opposite. Okay. And this angle is 90 degree. Now this is the first thing. The second step that we should be thinking about is drawing the forces or FBT. Now it is given that these masses are moving under their own gravitational attraction. So all we have to worry about is the gravitational force. Now since the configuration is symmetrical, we can just focus on one of the masses. We don't have to individually think about each mass because the FBT, the free body diagram, is going to be similar. So let's focus on this mass. What are the forces that this mass is experiencing? First is the attraction, the attractive force due to this mass. Okay. And forces act along the line joining the centers of the particle. So let's call this force F1. Now what are the other forces? The other forces will be due to this mass towards the chord that joins the two masses. Let's call it F2. And then this force which is along this chord. Let's call this F3. Now if you notice carefully, F2 and F3 are going to be equal in terms of magnitude because these two masses, this mass and this mass, is symmetrical with respect to this mass. The angle that the force is making is different, but the magnitudes are same. Since this length is the radius of the circle, this is also radius. So this is an isosceles triangle and this angle will be 45 degree. So let's simplify this. This is mass M experiencing a force F1. This is F2 and this is F3. And we just noticed that these angles are 45 degree. And the magnitude of F2 is same as the magnitude of F3. So let's try to find out the magnitude of these forces. First, let's focus on F1. F1 can be written as, using the Newton's law of gravitation, G m1 m2, the masses are same, m1 m2, upon the distance between the particle, which is d, that is 2r. Let's put the value of m and r, which is 1 each, 1 kg and 1 meter. So this becomes G upon 4. This is F1 and this is the direction. Let's talk about F2. Now we have already noticed that this triangle is isosceles triangle. This is R, this is R. So this is going to be root 2 R. So what will be the magnitude of F2? G m1 m2 upon r this time is root 2r squared. This becomes G by 2. And this force is in this direction. I'm just making it as a representation. Similarly, F3 is going to be G by 2, and this is the direction. Now the third step is to look at the vector direction of the forces. This is F2, this is F3, and this is F1. Now the forces are in different directions, so we cannot simply add them. We have to add them vectorally. Now since this angle is theta, let's break down F2 into vertical and horizontal component. So this is the vertical component, and this is the horizontal component. And similarly for F3, this is the vertical component, and this is the horizontal component. Now if you notice, the angle are same, so the vertical component cancels out because the magnitude of F2 and F3 is same, and the angle is also same. So all we are left is a force F1 and two horizontal component FH plus FH, and this resulting force is in this direction. So let's add everything up. So the net force, which is horizontal, is simply G by 4 plus 2 times FH. And how to find FH? FH is simply F2 cos 45. This is the force, and this is the horizontal component. This is theta, so this is cos 45. Let's solve this. We know F2 is G by 2 and cos 45 is 1 by root 2. So the net force is G by 4 plus 2 times G by 2 1 by root 2. And this becomes G by 4 plus G by root 2. So this is the net force. The problem is not yet over. This is the net force, and this net force is responsible for providing the centripetal acceleration to this mass towards the center of the circle. So the final step is to write the Newton's law. Net force is mv squared by r. So G by 4 plus G by root 2, mass is 1, radius is 1, simply this is v squared, or v is equal to root over G by 4 plus G by root 2. Now if we look at the options, the option looks simplified. So let's simplify this expression. So this becomes 1 plus 4 by root 2. If we take the root of this, we get 1 by 2 root of G. This is root 2 plus 4 over root 2. Let's multiply and divide by root 2 to rationalize. So we get G into 2, because root 2 into root 2 is 2, plus 4 times root 2 divided by 2. And this becomes, if I take 2 common, so G 1 plus 2 root 2. So this is the final answer. Let's check. So the final answer is option D.